The last video reviewed the basics of stoichiometry and how we can use the ratios in a balanced chemical equation to predict things like how many molecules of product we can make, or how many reactant particles we need to make a specified amount of product. But like I mentioned in the previous video, we are never just going to have one or two molecules when we do a reaction in the lab, and for that reason, chemists use a quantity called the mole. So to explain what the mole is, let's instead think about how we count other large groups of objects. So for example, eggs. So if you bought 3 dozen eggs, you would know that that is 36 eggs. Why? Because you know that 1 dozen is 12. And so 3 dozen would be 3 times 1 dozen, which is the same as saying 3 times 12. So that's how we would get to 36. So that's a way that we count eggs, which come in much smaller quantities than molecules do, but it's a really helpful analogy when we think about what the mole is. So if a dozen is 12, let's learn what a mole is. So 1 mole is 6.02 times 10 to the 23. So we use it the exact same way we would say a dozen, except to mean a much larger quantity of objects. And we could count any object in moles. So we could say I bought a mole of eggs at the store. It would be pretty unrealistic, but you could still use that as a number and a way to count the number of objects you bought. But in terms of molecules, we would never use a number as small as a dozen because we're always going to be using such huge quantities of those particles whenever we do any chemical reaction. So let's try an example where we convert a number of objects into the same quantity but in terms of moles. So here's a practice problem that we can work through. So it says the number of stars in the Milky Way galaxy is estimated to be around 250 billion. Approximately how many moles of stars are in the Milky Way? So the first thing we're going to do is remember that we are trying to figure out how many moles there are. So that means that if we're converting a quantity into moles, we need to remember how many objects goes in 1 mole. So there are 6.02 times 10 to the 23 stars in 1 mole. That's our ratio of stars to moles. So if we have 250 billion, let's just convert that to a number that doesn't have the word billion in it. So 1 billion is 10 to the power of 9. So what that means is that 250 billion is going to be 250 times 10 to the power of 9. So that's how many stars we have. So now let's think about what we would do if we wanted to convert this into dozens. So if we have 36 eggs and we want to know how many dozen that is, we would divide by 12. So we divide by the dozen. So likewise, if we want to turn this into moles, we would divide by the number that makes up 1 mole. So how that's going to work is we're going to say, well, we have 250 times 10 to the power of 9. That's how many stars we have. Then we're going to divide it by this quantity here, the 6.02 times 10 to the 23. And that is stars per mole. Stars per mole. So the units of stars will cancel, and we're left over with just moles. So remember how fractions work. If we have a fraction in our denominator, we can take this denominator quantity of mole and flip it to be just in terms of moles. And when we write the unit, we tend to leave off the E instead of writing moles. You can write the E if you'd like, but it's totally fine to just write MOL instead of MOLE. So the quantity that we end up with is actually still pretty startlingly small. So the number we end up with is 4.15 times 10 to the minus 13. So that's an extraordinarily small number of moles of stars in the entire galaxy, but that really just goes to put into perspective how small molecules are, and the fact that if we're using an entire mole of particles, that's a lot of particles. It's more than the number of stars in the galaxy by a wide margin. So the next thing that I want to talk about is the reality that scientists are never able to actually count the number of particles that we're using. So if we want to look at things in terms of moles, we're not going to look at the pile of powder in our sample and count out each individual atom. That would be impossible. The way that scientists measure things in the lab is usually by mass. So usually we will put something on the balance and figure out how much it weighs and then use that amount in our chemical reaction. So what we need to be able to do now is convert mass into moles. So this is the equation you're going to use to convert between mass and moles. So if you have the mass, you can calculate the moles by dividing the mass by the molecular weight of whatever substance you're using. So mass is measured in grams. Molecular weight is measured in grams per mole. So when you divide these, you end up with just leftover units of moles. So just a reminder, molecular weight, which is also known as molecular mass or molar mass, this is something that you can get from adding together the atomic masses on the periodic table for whatever elements make up your molecule. An example of this is hydrogen has an atomic mass of 1.008. So if we consider the molecule H2, it's going to have a molecular weight of 2 hydrogen atoms. So this is going to be 1.008 plus 1.008, and these are both measured in grams per mole. So that's going to give us 2.016 grams per mole as the molecular weight of an H2 molecule. So let's say we have 1 gram of hydrogen. So we want to know how many moles. So how many moles in 1 gram of H2? Well, the moles would be the mass, 1 gram, divided by the molar mass of 2.016 grams per mole. And what that gives us is 0.4960 moles of hydrogen. So the last thing that we're going to go over in this video is how we can apply the mole to stoichiometry. So specifically, if we have a question where we are given the mass of one of our reactants, how can we use that combined with our knowledge of balanced equations and molar ratios? How can we use that to predict other things about our chemical reaction? So here is a sample problem. It says you want to react 0.5 moles of H2 gas to make methane. What is the minimum mass of carbon that you need given the following balanced equation? So this is the same balanced equation we saw in the previous video, where we have a 1:2 ratio of carbon to H2. Since we have that 1:2 ratio, it tells us that if we have 1 mole of carbon, that means we need 2 moles of H2. Or vice versa, if we have 2 moles of H2, we need 1 mole of carbon. So what we have is the amount of hydrogen. We know that we have 0.5 moles of H2 gas that we want to react. So if we have that 1-to-2 ratio, we can do a similar type of calculation that we did in the previous video. So we have 0.500 moles of H2, and we want to use that 1-to-2 ratio to figure out how much carbon we need. So there is 1 mole of carbon for every 2 moles of H2. And remember how we set this up in the previous video? If hydrogen is in the numerator here, it needs to be in the denominator of our ratio. That makes it so that we can cancel those units out. And what we're left with is just moles of carbon in the numerator. So what this means is we're dividing this quantity by 2. So that gives us 0.250 moles of carbon. That's how much carbon we need for this reaction to go to completion. So that's in terms of moles, but this question says, what is the minimum mass of carbon that we need? So we can't just stop here and say, well, that was our 1-to-2 ratio. That's how many moles we need. Now we need to convert this into mass. So how we can do that is by using the equation we saw earlier. Remember, it said moles is equal to mass divided by molecular weight. We can rearrange this. In this case, we're solving for mass. We have moles. So what we're going to do is do a cross multiplication to isolate for mass. We're going to say mass is moles times, I'm just going to say MW for molecular weight instead of writing it all out. We need to make sure we have the molecular weight, but we do already have the moles. So we're just looking at carbon here. We're looking for the mass of carbon from the moles of carbon and the molecular weight of carbon. We don't have the molecular weight of carbon offhand, but remember, we just get that from the periodic table. So the molecular weight of carbon is 12.011 grams per mole. And that is from the periodic table on the element symbol for carbon. So then we can plug in, well, the moles, 0.250. The molecular weight is 12.011 grams per mole. And then that works out to give us 3.00 grams of carbon. And there you have it. So what we did was we said we need this much of carbon to react with hydrogen, and then we converted that amount from moles into mass. So that's it for now. You are going to build on these techniques in your first year chemistry classes. So you'll learn more complicated calculations related to stoichiometry. For now, you just want to make sure that you're comfortable converting between mass and moles and making sure you can go back and forth between them and understand why they're necessary for stoichiometry.